is Griffiths E&M section 5.2.2 magnetic fields and the Biot-Savart law. Okay, so in the first part of the course, we talked about how stationary charges created electric fields, and we recently introduced the fact that currents exist, and these currents are not changing in time, something we defined as being a steady current, and these are creating magnetic fields that we are going to calculate. In particular, these static charges generated things that we talked about in terms of electrostatics, and steady currents are going to make magnetic fields that are static in space and unchanging, magnetostatics. So things are still not changing in time. Okay. Just a reminder, a steady current is a current. Remember, a current is really just some charge distribution that's moving. Right? And if different pieces of that charge distribution are moving with different speeds, then you're going to have a current or a charge distribution that is changing with time and in space as well. Okay. So more generally, we're going to say that steady currents are where the time rate change of that current density is zero, and therefore the time rate change, the charge density is zero, and the time rate change of the current density is also zero. If that is true, we can go ahead and write the magnetic field from a current carrying element using something that's kind of like Coulomb's law, but is the Biot-Savart law. So from a steady current, I can calculate a magnetic field that exists at some location in space. I have some constant with a 4 pi. This constant is something you've probably seen before. It's the permeability. And the naught, the circle at the bottom, means it's of free space. This is related to the integral of our current, which is a vector, crossed with script r hat over the magnitude of script r squared, integrated along all of that current carrying area. You see this cross product in here. We're going to be doing a lot of right-hand rules. Remember that the current can be written, the current always follows the direction that we're always going to integrate along the current carrying path. So dl prime and I are in the same direction often. And with a steady current, we can go ahead and rewrite this as a constant, with the current as a constant, the magnitude of that current, as the cross product of our dl prime r hat over r squared. This looks a lot like Coulomb's law. Okay, so in general, we have some current carrying, let's say it's a wire, and it's carrying a current, we'll say it's going counterclockwise. I might want to find the magnetic field at this point in space here with respect to some origin. That's R. I have some arbitrary chunk of my current here. That's R prime, and again, we have script R like that. All right. So we can extend this to surface currents and volume currents. I'll have a question for that right here. And we can also use superposition. So just like if we wanted to find the electric field of something, we could always add up like vectors, different components. We can do the same for magnetic field. So if I have some distribution of wires going in different directions, all creating magnetic fields pointing in different directions. I can calculate the magnetic field from each of those and add them up as vectors.